Greetings. If you're just joining us, we're just getting started, and folks that have been signing in, hopefully you didn't have any trouble getting into the webinar today. We're just going to give folks a few more minutes, and we'll get started soon after the bottom of the hour from wherever you are. Good morning, good afternoon, good evening, and I know some of you it's late in the night, but you always tend to join us, and we really appreciate that. So again, sit tight, and we're getting folks to join us here for the next few minutes. Again, while we're waiting, just want you to know, as we're talking, you'll hear again later on, but our registration for IWCS 2024, the Cable and Connectivity Industry Forum in Providence, Rhode Island, USA, coming up in October. It's amazing. I can't believe we're already towards the end of July. But anyway, it's coming up fast, and you'll be receiving information about registration. So that'll be opening up next week, and hopefully you'll take advantage of some early bird discounts. So keep your eyes open for that. And we do really have a great program set up with a lot of great presentations, just like the one you're about to see. So a lot of good stuff. We hope you'll join us in Providence. So again, let's just give folks just another minute here, and then we'll go ahead and get started. All right. Well, let's get started. And again, welcome to today's IWCS webinar. My name is Dave Cadu, and I am honored to be the CEO of IWCS, and I'll be your moderator for today's event. Just a few housekeeping items. Please note that as an attendee, you're part of a larger audience, and so during the presentation, all participants will remain in listen-only mode. And also, this webinar will be recorded and available to you and your colleagues on our website here shortly, probably within a week or so. So if you want to share that, we will not be sharing the PowerPoint presentation to you, but at the end of the presentation, you'll see the email contact points for Carl if you want to reach out to him directly. We encourage you to submit written questions during the presentation using the chat panel. So on the right of your screen, if you hit the chat button, type in your questions in the space at the bottom, and be sure to hit the send button. And your questions will be addressed, time permitting, at the end of the presentation. Our IWCS webinar event is being hosted by the Cable and Connectivity Industry Forum. And again, today we're really honored to have Carl Sieben, Associate Research Scientist from Dow. He's in Pennsylvania, USA. Carl will be presenting his paper on fluoropolymer processing aid replacement in cable jacketing compounds, an important topic for a lot of future technologies that are happening. Carl joined Dow Chemical Company in 2011 and is an associate research scientist within Dow's wire and cable group. He holds a master's and a doctorate degree in polymer science and engineering from Lehigh University. Before joining Dow, he held various technical positions relating to polymer product R&D. His present research areas, in addition to processing aids, include both flame retardants and track-resistant polyolefin compounds for wire and cable applications. So again, Carl, thank you for joining us with this great presentation, and carry on.
Okay. Can you hear me okay?
Yes, absolutely.
Okay, so I'll get started here. I'm just going to describe on a high level here what I'll cover in this presentation. So basically, the first part focuses on poly and perfluoroalkyl substances. This in particular in the context of fluoropolymer-based processing aids, so it's very focused on that area. I will get into what the motivation is behind, why it's a good idea to avoid these types of processing aids, and what other options that can be used to replace them potentially. Most of this presentation will focus on dye buildup results, in particular for medium density jacketing compounds. I will branch out the results also to linear low as well as high density polyethylene jackets, and then I'll provide some of the key conclusions from this work. So processing aids, they're typically used in jacketing compounds because they have the potential to provide several key benefits, and they can include lowering extrusion pressure, improving the surface finish of the extruded product, lowering extrusion temperature, reducing gels. They can also, of course, help to reduce melt fracture as well as dye buildup. I will point out, though, that one particular processing aid does not necessarily provide all of these benefits. And so you do need to, select the processing aid for the particular need or for the problem that you're looking to solve. So really the two most common reasons why these processing aids are used in terms of jacketing compounds are to reduce melt fracture and reduce dye buildup. So melt fracture is basically flow instability that occurs within the dye, and that can lead to unacceptable surface finish. And so, like I show here in this picture, as you go higher and higher line speeds, this problem can, occur more readily and become more severe to the point where, you get this unacceptable shark skin type surface. Now, melt fracture can be addressed by resin design, so it's not always, solved by using processing aids. There are other, of course, factors that come into play. Dye lip buildup is another frequent issue that occurs. And so dye lip buildup is that unwanted accumulation or residue that shows up on the surface of the dye. Like I show here in this picture. And so what happens there is that, over time, throughout the extrusion process, this buildup gets more severe, and it's possible that the line may need to be shut down in order to clean, this residue off. If this residue becomes very severe, it can, of course, break off. It can plug up, extrusion cooling lines and so forth. It can also have an impact on the surface quality of the extruded product. And so, obviously, it's a problem that needs to be addressed. And this can be much reduced by the use of, certain processing aids. Now, unfortunately, dye lip buildup is a very complex problem that has many root causes. And usually, these I won't get into all of the potential root causes, but typically they're broken down into three main areas. One is machine related, which focuses on the dye, the design of the dye, both internal and external. It can be processing related, in terms of, temperature profile, how the material or the compound is extruded. But it can be material related. So in other words, the components used in the jacketing compound, or the resin in the jacketing compound, or both of which. Now, in this presentation, I will focus mostly on, or really pretty much exclusively on, the material related or the compound related problems that can relate to dye lip buildup. I will highlight one example here. One example I'll highlight is that if you, for example, have a high component of low molecular weight species within the compound, either coming from the resin or even the additives themselves, or the combination of the two, under high shear stresses within the dye, you can get a segregation effect. In other words, the low molecular weight species can get pulled off within the high stresses of the dye and then deposit on the surface of the dye. And so, that's one potential issue. Or, of course, the outside of the dye is relatively cool. So if you have, a high amount of volatile components within your compound, they can, of course, condense out on the surface of the dye. And typically what what a processing aid will do is it will change the profile of the melt flow through the dye. And so this would be the situation of the melt flow without the processing aid, where you have a lot of shear stresses that are occurring at the wall. So it's basically like a drag effect with high shear stresses. With the processing aid, it will even out, the profile and reduce those stresses. So that's one mechanism that can help, to avoid, the dye buildup, or at least help to reduce dye buildup overall. So now specifically about fluoropolymers. So fluoropolymer-based processing aids is a very common way to address or reduce dye lip buildup. And in particular, of course, there are many different chemistries, but the most commonly used ones are based on fluoropolymer chemistry. These types of processing aids have many decades of proven effectiveness, but they do belong to the category of per and polyfluoroalkyl substances, or PFAs. And I'm sure most of you, are familiar with that term. This is a huge category of chemicals having, a huge range of applications. And I won't get into all of those, but, they're in packaging, they're in nonstick cookware, and, other applications as well. They are, unfortunately, have a lot of EH&S issues associated with them. And in terms of the fluoropolymer-based processing aid, it's really the most commonly found one is the difluoroethylene hexafluoropropene. That's probably the most common chemistry. There are obviously different ones, and I'm sure most of you are familiar with the typical trade names for these types of processing aids. The issue with these things is that they're because of the highly stable molecule, the carbon-fluorine. They have the typical carbon-fluorine chemistry that doesn't easily break down in the environment. And so these chemicals are, very persistent in the environment. They have EH&S, health risks associated with them. And given that, this group of chemicals is so large, obviously there's a huge variety of chemistry, that are associated with these. So some are low molecular weight, some are high molecular weight. It turns out the low molecular weight ones are more, toxic, and have been studied because of that, have been more extensively studied versus the higher molecular weight ones. And the fluoropolymers that are used here are the higher molecular weight ones. However, despite these differences, these chemicals are all being lumped into the same category in terms of an EH&S perspective. In other words, high likelihood that bans will occur with these chemicals, and despite their EH&S profile again. And so given that, the objective of this work is basically to show that, there are other non-PFA based processing aids that can be used, that provide equivalent processing aid performance to these PFA type processing aids. And so they could be based on a range of different chemistries. They could be silicones. Some of these I will get more in depth in, and later in the presentation. Ones that we studied here, are silicone-based. There's functionalized polymers, stearates, waxes, and so these are all different non-PFA-based processing aids that were looked at in this study. So I already mentioned the potential for bans and restrictions. So here I'm going to briefly describe the materials that we used in this study. And so the table on the left shows the different processing aids that were looked at. And these, were based on some different chemistries, but we also looked at two different typical fluoropolymer-based processing aids, which I've abbreviated as FP1 and FP2. These are pretty typical ones. But we also looked at and compared the performance of those to some non-PFA-based processing aids that were silicone-based, such as silicone oil, functionalized silicone oils, high and low molecular weights. Also looked at a polar polymer additive, as well as a blended system of a silicone oil with a polar polymer additive. These compounds were, produced in a melt mixing process. The table on the right is basically, there's a lot of information here, but basically, what I'm showing here is that, we mostly concentrated on medium density jacketing compounds. That's where most of the studies that I'll show here are. And so this is looking at, how these different processing aids perform within the medium density jacket compound. But we also expanded out to linear low as well as high density jacketing compounds as well. So basically, these are just the different combinations, jacketing compounds with various non-PFA based processing aids. Okay, so the first part of all of this work was to basically ensure that we had an effective test method, to evaluate dye lip buildup. So here I'm basically describing, a high level here, what this method was. And so basically this consists of a single screw extruder with a typically relatively small dye tip, 0.06, where we captured, pressures as well as temperatures, and of course the dye lip buildup over time. And so the dye lip buildup is captured at set, time periods up to 3 hours overall. And so also in order to evaluate, the dye buildup itself, we developed a rating scale of performance, basically 1 through 5, with 1 being no buildup, like I show here, versus a 5, which would be severe buildup. Throughout this test period, we also captured some other parameters, such as output rates, strand diameter, and so forth, to ultimately, evaluate processing aid performance. One other thing I'll point out here is that we did take a lot of precautions in this test to adequately, actually, I will also, before I move on here, is in this rating system, based on, multiple runs and experience and so forth, we did establish a target performance where basically a 1 or a 2 is what we're really shooting for in terms of, meeting the desired performance for dye buildup. But the other thing I want to point out here is that we did take precautions to adequately clean, the extruder and all the tooling associated with that between samples, so as to remove, buildup. A lot of these processing aids do, build up on the tooling, and that can remain on the tooling even after that processing aid is no longer present. And so that was precautions were taken with regard to that. Okay, so I mentioned, so here I'm going to now focus on some of the results in terms of dye lip buildup. And again, most of the focus of the study was on medium density jacketing compounds, so I'll go through some of those key results. So the table here on the left captures the dye buildup performance over equal time periods. MDPE1 was a control sample or comparative sample. So basically just the polymer itself. And so in that series of pictures, you can see that, the buildup occurs quite rapidly with the onset occurring, within 5 minutes. And overall, there was quite severe buildup at the 120 minute with a rating of 5. MDPE1 BK, so that's the next series of pictures I show here. That is basically a fully formulated jacket compound, but with no processing aids. And so the overall, the buildup is about equivalent to the first series of pictures, having an onset time of buildup of about 5 minutes. And so this basically is suggesting, pretty much that the polymer is contributing significantly to the dye buildup overall. The last series of pictures is basically a comparative sample. That's the fully formulated jacketing compound with the typical fluoropolymer-based processing aid. And so, as expected, this shows virtually no buildup over the entire test period. And so this is kind of just showing that, this test method can provide relative performance differentiation between samples within a relatively short amount of time. Okay, so here now I'm showing dye buildup results for some of the non-PFA-based processing aids that were studied. The first series of pictures in the table on the right here is an alternate fluoropolymer FP2 that we looked at, and as can be seen in the series of pictures, this shows very poor performance. And so this highlights that, not all of these, even the fluoropolymer-based processing aids can address the dye buildup or have an effect on dye buildup. And so going back to what I said earlier, depending on the system, the compound itself, not all processing aids can, solve or provide every benefit that is necessarily claimed. So the next series of pictures is MDPE1 BK-SI1 that showed very poor performance. That's basically a high molecular weight silicone oil. And so that, had a relatively short onset time of buildup of about a minute. And then MDPE1, FSI2 and 1, those are functionalized silicone oils where we saw with the higher molecular weight functionalized silicone some effectiveness in reducing dye lip buildup versus the lower molecular weight version, which did not show any benefit. Finally, the last series of pictures is a polar polymer additive, which did show very good performance, and that performance is about equivalent to the FP1, which was the other fluoropolymer additive that I showed on the previous slide. So this graph here on the left is basically capturing the dye buildup performance over time over the entire 3-hour test period. Yeah, I'll point out a couple things here. That comparing the dye buildup of the base resin MDPE1 to the fully formulated MDPE compound, which of course this one has the no processing aid, indicates that the additives actually in the fully formulated compound did actually contribute to increasing the rate of the buildup. And so those additives increase the rate of the buildup either, by, that forming or the additives themselves contributed to the buildup. The traditional fluoropolymer, of course, showed very good performance, and also highlight the polar polymer additive showed good performance in comparison to that. So this picture here, or graph on the right, is basically a summary of all of the medium density compounds that were looked at. And one thing I'll point out is that we looked at the results for the polar polymer additive, which I mentioned, showing good performance. We looked at that at 2 different concentrations, and we did see a slight improvement in reduced dilute buildup at the higher concentration versus the lower concentration, showing basically a rating of a 1 versus a 2. As I mentioned, the functionalized silicone did show some effectiveness, but overall was not as effective as the polar polymer additive at the same concentration. Okay. So here, what we did was we took selected examples or samples of these medium density jacketing compounds, and we evaluated those in a full-scale wire extrusion coating line. Here I'll point out a few things. I show, breaker plate pressure, melt temperature. So basically, these results are showing the typical fluoropolymer had similar pressures to the control sample or comparative sample MDPE BK. That's the sample without processing aid, and also similar to the polar polymer additive sample. These results basically indicate that the fluoropolymer did not significantly, reduce pressures overall, but neither did the polar polymer additive. Extrusion melt temperatures for the polar polymer additive sample were similar to the fluoropolymer containing samples. These results pretty much indicate that processing should be similar with the polar polymer additive sample versus the comparative with the typical PFAS-based processing aid. So these same samples that I showed in the previous slide were evaluated for dye buildup as well, but this is now evaluated in the full-scale wire coating line. We use the same, rating scale that we established for the lab scale dye buildup test. And so here I basically show a side-by-side comparison of those results. And so one thing that we saw was that the lab dye buildup test was more severe overall versus, the full-scale extrusion process was a lot more forgiving in terms of dilute buildup. And so the lab scale test was, more useful for, these initial studies for screening experiments overall versus what we found with the full-scale wire extrusion line. The other thing that we saw was that this promising polar polymer additive showed similar results to the fluoropolymer, the typical, fluoropolymer containing sample. And overall, these samples showed about equivalent jacket smoothness. So really no, melt fracture issues would be expected with the modified sample with the polar polymer additive. So here, I'm not going to talk a lot about this, but, we did look at some rheology, tests for these samples. And so I'm showing both high shear rheology test results that were conducted in a capillary rheometer on the left, top left, versus a lower shear ranges tested in a parallel plate rheometer. And so we did not see, a lot of significant shifts in viscosity, in this comparison. We did note slightly lower viscosity in the capillary rheology results for the sample with the higher concentration of the polar polymer additive, but overall, these differences were quite small. So the capillary rheology test was also used to evaluate the samples for melt fracture. And so I'm showing those results. And so what this is basically capturing the lowest shear rate at which, signs of flow instability show up for some of these samples. And so MDPE1, is our polymer, comparative polymer sample. As we start to see flow instability at 1076 1/2 and then as we go to the fully formulated jacket compound MDPE1 BK, there's some improvement there, as can be seen in the pictures. You do have to kind of look a little bit closely, but you see the flow instability in the strand itself at a slightly higher at a higher shear rate. That's likely due to the fact that the fully formulated jacket compound does have a slightly different additive package coming in, which plays a role in how the compound flows through the capillary. So that's likely what's going on there. Then as I move to the third series of pictures here, MDPE1, BK, FPE. All right. That shows further improvement in flow stability. As you can see in the picture, you have to look a little bit closely there. There is some flow stability at the same shear rate, but it is slightly improved versus the sample without the processing aid. So moving to this series of pictures, we looked at the higher concentration for that, and we saw even further improvement there. So flow instability showing up at 4,680. And then finally, the bottom set of pictures here is comparing the fully formulated jacket compound with the typical fluoropolymer-based processing aid, and we actually saw a slight improvement versus our modified compound with the non-PFAS based processing aid. So here, what we did was we looked at the dye buildup sample itself. And so we wanted to basically get a better understanding of what was going on with the buildup. And so in the case where we were able to collect enough material of the buildup from the actual extrusion process itself, we tested that in GPC, characterized it, the molecular weight distribution by the GPC. And what we found was that comparing the buildup versus MDPE1, MDPE1BK, the buildup does show a relatively high amount of low molecular weight species with a PDI of 6.3, so reduced PDI of 6.3. Comparing the comonomer distribution of the buildup versus the comparative samples, those aligned, and so that points to or suggests that this buildup is likely material coming from the original resin. So in other words, this is not degraded buildup. And so the other thing I'll point out here was we did ensure that our sample was not cooking, heating on the face of the dye for extended periods, and so to avoid the effect of the oxidation from that end. There's also high molecular weight components present, in the dye buildup itself, and the dye buildup is really mostly the polymer. Overall, this result is consistent with studies that you can find in journals and in literature and so forth, where they have found similar results. In some cases, you can get degradation, and that was found as well. So on here, so here, given the good performance we saw with the polar polymer additive, as I mentioned, we extended out, investigated this same additive in a linear low density jacket system, and I'm sort of capturing basically those results here. So the series of pictures here on the left is again a comparative sample, and this is the comparative sample with no processing aids, so fully formulated jacket, and we see typically very high amount of buildup throughout at the end of the time period, with the onset of the buildup is quite rapid actually. And so this middle series of pictures I show here on the right is the series of pictures with the typical fluoropolymer additive. And so there's, as expected, there's very little buildup throughout the period that we're testing. And then finally, the last series of pictures is the series with the polar polymer additive at that same concentration as what we used in the medium density studies, and that works as can be seen here. It's very effective and actually slightly improved. So we also extended out this approach to high density jacketing compounds, and so we looked at two different high density base resins, one slightly lower in density, the other HDPE2 with slightly higher density. The HDPE1, again, actually with no processing aids, we do see some buildup. It's not as severe as what we see with the linear low and the medium density. But then we looked at the performance with the typical fluoropolymer processing aid. It's roughly the same. It may be slightly worse. And then with the polar polymer additive, results look very good overall. With the high density HDPE2, this is a little bit higher density. We looked at two different concentrations, and we saw, comparing with no processing aid, you do see that improvement, and we did see actually slightly better performance at the higher concentration of this polar polymer additive versus the lower concentration. Okay, so here I'm not going to spend a lot of time on this, but this is just basically to show that we did more extensive testing, given that we saw a good performance with the polar polymer additive to evaluate, in particular, heat aging and more longer term aging performance of a compound with the polar polymer additive versus what you would have with if you formulated with a typical fluoropolymer additive. And so overall, we achieve basically similar performance, and we can still meet all of the typical jacketing property requirements that you need to meet for medium density jacket. In particular, as I mentioned, the aging performance overall, and there were other properties that were looked at that I don't show here, electrical properties and so forth, where we were also similar overall in performance. So here I'm just going to kind of summarize, what we conclude here from this work. So I think the big picture is that obviously the fluoropolymer-based processing aids, they perform very well, in particular for reducing dielet buildup. However, if you can select non-PFA-based processing aids that will work equivalent, and in some cases, perform slightly better, at least within the context of this study. we identified one in particular that performed, extremely well and compared it to, the typical fluoropolymer additive. And I'll highlight that, these processing aids do need to be carefully selected, since, depending on what problem you're looking to solve. Rheology tests were about similar performance versus the typical fluoropolymer processing aid, and even going into, the full-scale wire extrusion processing, we achieve about similar, processing performance at that scale as well. We also extended out, this testing to linear low as well as high density jacketing compounds, and we're able to show, the same benefit that we saw with medium density jacketing compounds. And so, that's pretty much what I have here. I guess we can stop here and open up to questions at this point.
Carl,
Yeah.
thank you very
Yeah.
much. A lot of really good research and understanding in different types of polymers. Just one thing that I noticed in the discussion of PFAS, I think we need to make sure we distinguish between PFAS chemicals, like these processing aids compared to the fluoropolymers themselves. I mean, a lot of discussion going on in the circles of dangerous PFAS materials versus the full fluoropolymer technologies. So we just need to be careful because it could be confusing as to what's a good PFAS and a bad PFAS. So I just wanted to bring that out to our collective attention. Several questions. I know your work was focused heavily on polyolefins and polyethylene in particular. Do these processing aids also apply into other compounds such as PVC jacketing compounds?
I honestly have to say I don't really know for sure because our, study was focused heavily on polyolefin-based compounds, and I can't say with enough certainty or comment with certainty on how they would work with completely different polymer systems. So fortunately, I, can't answer that directly.
Fair enough. Are the melt temperatures of the polyethylene jackets changed at all by using different polymer processing aids? For example, does the polyethylene jacket melt at a higher or lower temperature, based on the processing aid?
Well, within the scope of our study here, the one I'm presenting, I did not see significant shifts in melt temperatures. And of course, we also looked at melt temperatures within wire extrusion processes, and I didn't see large shifts in that from that regard. So yeah, I mean, I would say, given the processing aids that were looked at within my study, I didn't see large changes in melt temperatures.
Okay. And similarly, I guess, do the various alternative processing aid materials have any impact on, say, fire performance in the final cable or any other characteristics?
No, I would say in that context, no, because these processing aids are going in at relatively low concentrations that I wouldn't expect impact at all. So whatever fire retardancy you had, initially, it would be about the same as what you would have with the slightly modified, regardless whether it's the PFA versus the non-PFA, because in both cases, those processing aids are used at relatively low concentrations that I wouldn't expect to change from that regard.
Right. Besides the empirical methods that you used in looking at different effects, Can you share if you have evaluated any digital modeling that can be utilized to predict, dye buildup performance? And if so, what might be the main factors and outputs?
Uh, well, I did not look at that, but there are plenty of studies in journals and in the literature that do focus on that, that specific area where the idea is to model, the geometry of the dye, for example. I've looked at, read several studies along those lines where, you can model, of course, like I mentioned, the geometry, the L over D of the dye. There are many factors that will come into play, like the surface of the dye itself. And there are studies on that as well, the coatings of the dye, whether they have, low surface energy coatings or they have different metallic coatings. The studies have shown some effectiveness with that. But, in terms of the modeling, some of the modeling also focuses on the particular geometry at the outset of the dye. And so, there's patents out there where claiming that in terms of, in particular with external dye buildup versus the internal dye buildup, that's changing the geometry on the outside of the dye can have an impact on that. And of course, there's other patents out there where, they attempt to reduce the buildup by applying different, recesses or, ways to remove that buildup externally without having to, physically stop the extruder, that type of approach. But again, in terms of my studies, I personally we did not take it to that particular area. That I believe that's what you're asking, at least here.
Yep. Just a couple more questions. Would behavior be expected to be the same or different with larger diameter dyes? Say example 2-inch dyes.
Well, I mean, yeah, yeah. I'll go back to the previous comment that I made, in one of my slides, is that unfortunately, dye buildup is extremely complex, and it's going to be. And I know it sounds like a cop-out answer, but it would depend on many factors. And you probably have to look at the particular circumstances and all of the different parameters that you're focused on in terms of your particular process to in order to provide a reasonable assessment of whether that would make a difference or not. There's generally, they say, if you L over D, lowering the L over D could reduce dye lip buildup. That's commonly seen, like in papers, and it's been studied that, but again, to make a blanket statement is a little bit hard to say because there are so many different factors that come into play. We would probably have to look at it more carefully to give a better answer for that particular situation.
Yeah, and in terms of long-term jacket stability, have there been any, life cycle testing studies to determine the effects of these polymer processing aids, just in terms of jacket stability over time?
Talking about the jacket, the jacket itself, I guess. Aging studies on the extruded jacket. I believe is that what you're asking, or?
Yeah, I think it's really, do the processing aids do anything to affect the stability over time? Whether it be migration, whether it be any kind of effects, or does it need to be studied? I mean, it doesn't. It sounds like we need to understand that a little bit further.
Yeah. I mean, that's one area that we could look at. And again, the study that was done here that I presented, we didn't look at specifically that. Now we did, of course, look at what's typically required, in terms of specification, in terms of what typical jacketing compounds is required in terms of aging performance, like age, tensile, and elongation. ESCR, those are long-term aging effects. We look at OIT, those types of things. But specifically, long-term aging on the extruded jacket, I have not looked at in this study. That could be an area for further research, further probing, and further experimentation. Yeah, definitely could be an area that we could do more work in.
Right. And one last question, just relative to the perfluorinated processing aids, the control, if you will, are the loadings similar to the alternate polymer processing aids? Or do you have to modify the
Yeah,
concentration?
yeah, it's a good question. They're actually in a different range. The overall the loadings of these processing aids that were looked at within this study that I'm presenting here are higher, but overall, as a percentage of the full formulation, it's still very low. The fluoropolymer processing aids are known to be effective at very low levels, 200 ppm, 100 ppm, 500 ppm. But a lot of processing aids, it's very common for those to get up into the 1% range, 0.5% range. So a little bit higher, but still overall percentage wise, relatively low. If you look at all the other components that are going into the compound, because remember, we're putting antioxidants in, we're putting carbon black in, and blending it in with sometimes other polymers into, so it's a blended system. So yeah, I mean that's how I would look at that. Just keep that in mind that the fluoropolymer, those are typically used at very low levels.
Yeah. And if you use the alternate, the FPE one, I think you called it, processing aid, does that show up, if you do an FTIR or something like that, does that show up in the chemical fingerprint? Or does the fingerprint change at all?
Well, that is sort of again another. It depends, if how in depth and how it could potentially, but it may not either. Again, the levels are very low in it, so it's one of those things where if you're analyzing in ppm level, you could potentially see the fluoropolymer. Possibly, you could potentially see anything if you take it to the level, analytical level of ppms, low concentration things, and that it's always possible to potentially decompose something into its basic components. So yeah, that's probably my best answer on that one. It's just going to depend how you do,
Right.
how you do the analysis, what you're looking for.
Sure. Well, thank you, Carl. Again, very interesting and important topic, and we appreciate the audience providing, very insightful questions. Please note the contact point that's being shown here should you wish to reach Carl after today's event. Again, as I mentioned, this presentation, as well as all of our webinars, are recorded and are archived on our IWCS.org website, and as well as our YouTube channel. So you can find them there if you want to revisit and share them with your colleagues. The IWCS webinar series will conduct its next technical paper presentation in August, on Friday, August 16th. It's typically the third Friday of each month. at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for that event. And again, please feel free to share these announcements with your colleagues so they can join and register as well. And speaking of registration, I'm very excited to say that our IWCS 2024 Cable and Connectivity Industry Forum is coming together. I can't believe it's only a few months away, but you'll be receiving information on registration here shortly. Also, I want to recognize and be sure that we express our appreciation to the contributions of our partner level sponsors. Without their strong leadership and generosity, we would not be able to bring these important technology innovations and information to you and our global community. So again, thank you to these leading sponsors, including Dow. Again, I want to say keep your eyes open for more information. We do have a preliminary program. It really is a comprehensive program for technical presentations and a number of important trends and assessments on what's coming for the future. So please try to attend in Providence, and you'll be able to access all of that information on our website and also through the announcements that'll be coming your way. So keep an eye on your inbox and your social media as well. And again, make note of the date. We're actually conducting the conference on Monday through Thursday this year. That's the way we did it a number of years ago. So hopefully that'll allow for your travel arrangements accordingly. So again, thank you to Carl, and we wish you a fun and enjoyable summer weekend. All the very best. Thanks.
Thank you.